Good morning and welcome to this morning's seminar given by Regenesis and Haida, presenting a case study on the treatment of high concentrations of solvents and DNAPL under an active industrial dry cleaner in the United Kingdom. This morning's webinar is presented by George Flower of Haida, the consultant for the project, and Gareth Leonard of Regenesis, who's a design engineer for the project. And we'll cover a variety of issues related to the project based on the concept, the monitoring, and of course the treatment. There are a number of interesting points, I think, about this case study, but I won't steal the speaker's thunder. But it does provide a good example of the full capability of biotreatment and how that can be used under relatively restricted conditions to great success. A bit of housekeeping before I pass over to George for the first part of the talk. You will be able to hear me, but we won't be able to hear you, as all microphones are muted, simply so that any background sounds that there may be in the various offices and computers listening to this don't interact with the sounds of the webinar. If you have any questions, therefore, please use the little screen on your dialogue, in the dialogue box that you should have up, to type any questions that occur to you at any time through the presentation. These we will collate and we will answer as many as we can at the end of the session. If we are unable to get through all of them, we will endeavor to get back to any of the unanswered questions within about 48 hours. So without further ado, I'd like to pass over to George Flower of Haida for the first part of this case study and setting the scene. George is the technical director for Haida Consulting. He's a geologist by principal training and has over 25 years contracting and consulting experience in the UK and overseas. This spans civil, geotechnical, hydrogeological, and also contaminated land, which is presently what he's working on principally for a number of clients across the United Kingdom. George is based in Bristol in the UK, where we're giving this webinar from at the present point of time. And without further ado, I'm happy to pass over to George for the webinar. George, over to you.
Okay. Well, hello everybody. George speaking here. Thank you, Jeremy, for that introduction. Yeah, if we go to the first slide. What I would like to run through this morning is the reason the project came to be, which was a spill of dry cleaning fluid. Run through the site conceptual model, which is a key part of the project, as we undertook a peer review of another consultant's work and subsequently took possession of the project to move it forward. Just like to run through to remind ourselves of the nature of the contaminant, the perchloroethene, and that helps inform the risk assessment choices that each remediation project requires one to think about. Looking at the basis as a risk-based corrective action, and then reviewing the enhanced natural attenuation that I know Gareth will be talking a little bit more about later on. Principally, we employed a micro-purge bladder sampling system, which was quite instrumental in improving the quality of the knowledge and quality of the groundwater testing. And from my standpoint, a few years ago, I would have thought that sampling groundwater was very straightforward and easy. You know, yes, there's quite a bit written about different techniques, but how much difference would they really make? Well, I think I'm completely convinced that in certain circumstances they make a phenomenal difference and they're very important. So we'll just review those at the end before I hand over to Gareth. Okay. That's just a picture came up there of one of the application rigs inside the working premises, so you can see it's very constrained in terms of access, but nevertheless we cause minimal disturbance to the business and let them get on as usual. The problem resulted from a delivery, happened over 20 years ago, of a delivery of PCE. It was estimated 20 tons were lost, the majority left site in the drainage system. And it was estimated that 2 tons resided in the ground. Yeah, so I know Gareth will talk a bit more about the site circumstances. Just a quick reminder, PCE is 1.6 times the density of water, and it's also about a fifth of the viscosity of water, so when it enters the ground it tends to sink, and once it hits the groundwater, unlike a normal hydrocarbon, it doesn't float, it sinks. hence the expression dense non-aqueous phase. And the groundwater was significantly polluted with and free product. The other consultant had done a good site characterization, to be fair to them, and had noticed that the free product resided in these yellow silty sand, fine sand lenses within a series of glacial till. There was a bedrock condition, so we knew the base of the problem, but with the green areas here were clear evidence of free product, and the groundwater sampling showed that significant impact in the area. This is a UK Environment Agency publication. I'd really recommend it. It's a very well written, very understandable, and I've put it in here to remind people of the nature of this contaminant, particularly the diagram here over to the right. In fully saturated condition, the product likes to form globules and ganglia, as they call it in the EA publication, that sit locked into the soil structure, and it's relatively insoluble, but soluble enough to cause a problem. So this free phase will go on releasing pollutant to groundwater for many decades if nothing's done about it, and that was the situation at this site. Although it was 20 years ago, very little degradation was actually happening. Migration was slow, but there were houses to the south of the site in the groundwater direction, and the risk assessments that we inherited said that this was a risk to housing and from vapor release from groundwater. It was noticed that degradation was occurring in the PCE, but it was very slow, and the risk model, when we came to review the job, predicted an unacceptable risk to homes, and that's what triggered the next stages of the project. So the knowledge of the site was that there was a low dissolved carbon, and that's known and written up in quite a few publications that would limit the reductive dechlorination. What was noticed is where there was a diesel spill that reductive dechlorination had happened in one area of the site, so we had confidence that the bacterial populations were present, but there was little of that where the main free product existed. And when there's no degradation, the product can migrate off-site for great distances, and that's really what drove the risk to be unacceptable. And because of the little degradation, to clean the site up enough to protect those houses in that model, a very stringent remedial objective was being put forward, and the previous consultant concluded that the clean-up required to protect the houses was unachievable by in situ methods, and they had run remedial trials of pump and treat and also vapor recovery, but in the very fine-grained soils they found that that wasn't going to be sufficient, and the client was actually facing an excavate and replace system, so dig and dump in simple language. But because of the constrained nature of the site, that was going to be a very high geotechnical challenge with driven sheet piles and working with tented enclosures and people, digger drivers in positive protection suits and things like that. So we were brought in for a review, and one of the questions that the site posed to me was, well, if we can increase the rate of degradation, how would that affect the risk model? And when we ran those risk simulations through, what we found was that the remedial objectives actually didn't have to be so stringent, and in fact, as long as we could degrade the free product to less than 1% of solubility, we would actually achieve the protection of the houses because of that increased rate of degradation. We knew that depletion of DNAPL was possible in situ, and therefore we ran through that process and talked to the client, and to cut a long story short, realized that an enhancement of the degradation by a hydrogen release compound was very likely to be successful, and that's what we adopted. So the key benefits to the client were that there's no excavation costs and risks, no risk to their structures and to party walls, no nuisance to the residents behind, and all landfill disposals would be avoided, so a significant benefit. I know Gareth's going to talk about treatment areas on the site, so I'll let Gareth do that. I won't dwell on that too much here. Really what I want to focus on is the monitoring system that we adopted, and with natural attenuation, whether it's enhanced or natural, purely natural, the verification and sampling of the groundwater is the absolute proof that you've got that you've been successful. So we developed a multiple lines of evidence base with the Environment Agency that yes, the reduction of DNAPL was the prime objective, but we agreed lots of other lines of evidence based on the Environment Agency's own documentation, and also so the key parameters like the oxygen reduction potential and dissolved oxygen were collected during the project. The field measurement of certain parameters is essential, And with the pneumatic bladder pump, we ran a multi-parameter probe in line with the sampling to enable consistency and repeatability of results. And it resulted in a data set that we completely had faith in. We know, we went there and collected it. And it was important for the client because they needed reassurance that a system that you apply something in the ground and then have to wait a certain length of time for it to happen, that's a big leap of faith for a client sometimes, and therefore we adopted a pay for performance, which Regenesis accepted, that there was a stage payment for stage benefits, and that also helped inform the regulatory confidence in what we were doing and their sign-off, and it met our clients' core objectives. I put this graph up. The main things to focus on are the green bars is the data set that we inherited from the consultant. We don't know exactly the form of sampling, but I suspect it was a 3 times well volume system, either with Volterra tubing, foot valves, or perhaps with balers. And the blue is the results that we obtained with bladder pump sampling. And I think the key things I would like to say is these are 4 sampling wells. 301 is actually at the source zone, only a metre or so from the tank that deposited the contents in the ground. But if we come to the left here at 205A, there's a result here of 63,000 on one monitoring event, and then the same consultant went another monitoring round and got 492. Well, that's not a change in the actual groundwater results. That's the same groundwater, and therefore these results ought to be showing pretty similar results. And when we went to that sampling well, and basically it would have been the same groundwater, these are the results that we achieved, about 1% of the solubility. And I put the red bar up here just to remind us of the limit of solubility, variously quoted, between 170 and 200 milligrams per litre. So you can see with the sort of 3 times well volume, the difference in results that you get from what should be the same groundwater. And you can see what we've got when we do the bladder pump, which I believe is actually pulling in the true dissolved phase of the groundwater. This result here at 420, clearly that isn't just dissolved phase in the groundwater. That is clearly brought in some globules, some free product into what should be a groundwater sample. And of course, when you send that to the lab, they will report what you send to them. They won't make an assessment of whether there are globules in there or not. That's not their job. That's our job as consultants in sampling. So there's very clear evidence that purge method does bring in variously a free product. And it was only when we've sampled right up close to the spill event that even with the bladder pump system, there was clearly major impact to the groundwater. A key benefit with the bladder pump system, we believe, is the ability to obtain in situ parameters at the time of sampling. And this is after the hydrogen release compound had been injected. And I know Gareth will pick up on this later. But very interesting that when you run the micro purge, the guidance requires you to run the micropurge until the key parameters become consistent, and a benchmark of plus minus 10% is given in terms of when you're confident you're pulling in water from the aquifer rather than water which is stagnating in the well. And I think what can clearly be seen here is that the HRC has achieved a very low dissolved oxygen. Critically, it's also the pH is not plummeted, and I know from the research we did that other treatments have sometimes suffered that problem with a plunging pH, and the oxygen reduction potential is just fairly gentle but gone negative down at about -20, -30. And the consistency that this system gets is really enhances the confidence that we've achieved what we set out to achieve on this project. I know Gareth will look a bit more detail at the concentrations, but what I found interesting, and I know from speaking to other people in the industry, that the historic sampling had obviously recorded some free products, so up to 200,000 micrograms. From a contract point of view, we settled on a baseline of about 45,000. But what's interesting, and is what's Jeremy's in talking to him, when the bacterial degradation starts to advance, you get at microbial level, you get the mobilization of your contaminant back out into the groundwater. And obviously, although that makes it look like the situation is getting worse, to actually cure it, you need to get the solvent back out into the groundwater. And then, so that's what it achieved. And then once the monitoring started, you can see how the depletion of the PCE. And remember that the only thing in the ground was the PCE, and they'd been there 20 years and very little degradation had happened. So this is the only source material there. And by the time we did the last two results here, PCE was at below level of detection. So the lessons learned, the sampling significantly influences the measured concentrations. With a high purge system, perhaps our Baylor or a football system, the sample is groundwater, yes, but it's variably and randomly plus minus DNAPL if you're in a DNAPL area. This therefore gives you data that makes you overestimate the risk, and if you're overestimating the risk, you overestimate the remediation required, and that's an excessive cost to the client. I think one benefit, and we've used this on another project recently, is sometimes deployment of that system is good if you need to double check the presence of DNAPL. So sometimes that form of sampling is good to do, but that result is of trying to sample DNAPL. It is not representative of the groundwater, and you need to make sure that you label your samples and the logic behind it accordingly. The micro-purged pneumatic bladder system, I think it gets as close to a true groundwater sample as you can get, the dissolve phase. And by the micro-purge, it tends to not violently disturb the formation, so you don't mobilize DNAPL that might be stuck to soil grains. The migration risk is far better informed, and that leads to a more focused remediation and often a lower cost remediation, and opens up more options. We used a dedicated system on the site because we knew we were going to be monitoring for at least 12 months, and it ended up to being 18 months. And it gives you consistency and believable data that the regulators can also have faith in. And that gives everyone high confidence and the verification of success on the project. So I think now I'm handing over to Gareth to tell you a little bit more about the treatment.
So this is Jeremy again of Regenesis. To introduce Gareth Leonard, Gareth is the UK and Scandinavian District Manager of the Regenesis European team. Has worked in the industry for, how long is it now, Gareth? About 12 years. It comes from a geological background principally, but also with a master's in environmental chemistry, and has worked his way from the oil rigs through the remediation contracting fraternity, and for the last 7 years I think has been working in Regenesis as a design engineer and effectively advisor and question answer to a range of clients across the colder swathes of Europe. Gareth is with us now, and we'll talk now more about the chemistry and the technology of the treatments and open the box a little bit more into what was really going on at the microbial and chemical level. So over to you, Gareth.
Thanks, Jeremy. I don't mind the coldest swathes of Europe. I'm from the north. It doesn't matter. Okay, I'm going to talk about this site a little bit more. I want to talk about the distribution of the contamination on the site right back from when it was spilt to what we were actually dealing with. It's important because we chose different methods and different products in order to deal with the contamination based on where it was and in what concentrations. The process we used was enhanced reductive dechlorination, so I just want to go through the science of that a little bit, go through the products that we used. I'll show you some of the application in terms of photographs from the site, and then go through a couple of the results on the site, showing you some areas where there was low concentrations that we dealt with and areas where there was DNAPL that we dealt with as well, and then go to a conclusion there. So if you're looking at the site here, on the left there is the building. It's active industrial dry cleaners, so a very large facility. It's taking in a lot of laundry from hotels, etc. A lot of very large machines in there that is using the PCE, or had been using the PCE, to do dry cleaning activities. Busy all during the day, all during the week. On the outside, on the right of the site there, it's perhaps about 10 meters wide, this yard, by about 30 meters long, 40 meters long, where we were dealing with it. Is where they get deliveries and can be quite busy as well. So if you look at the top there, this is where the spill source was. There was a tank attached to the wall of the building, and they filled it up, but they'd left open one of the taps, so it just came straight back out again. Quite a large spill, and as George said, about 2 tons went down into the ground. The groundwater flow is down to the right there, down to the southeast. Essentially, the contamination moved down under gravity into the granular-made ground beneath the site. Underneath the granular-made ground are very tight clays. Within those clays are sand lenses. Still pretty low permeability, but we've got an upper and a lower sand lens in which the contamination tends to have sat. It's the easiest place for it to get into, and it's gone to that location. The concentrations were suggestive of DNAPL, but it's very difficult, as you may know, to actually sample a decent amount of DNAPL. DNAPL doesn't tend to pool as such. As George mentioned, you tend to get globules and gas. Essentially, the product doesn't want to be in the groundwater, so it does its best not to be in the groundwater, and it will sorb, or you'll get globules. The other thing that happened is that the site actually slopes down to the right there, so a lot of the contaminant, when it was being spilt, went across the surface into that ACO drain you can see going down the center of the site, went down that drain. The drain's not in the best repair, and it leaked out from cracks in the drain and got into the clays and sand as well. Further down. So we've ended up with very high concentrations across quite a wide area rather than a confined source area. The PCE went down to about 10 to 11 meters below ground level. Groundwater is about 2 to 3 meters below ground level, mostly clay, and you've got these two areas of sandy lenses. What this means is there's a highly impacted zone up to about 150 milligrams per litre PCE. Quite difficult to tell exactly how much was in there, because a lot of it was in the form of DNAPL, as George mentioned. And as I say, the product doesn't want to be in the groundwater, and you're sampling groundwater to see how much is there. So essentially, you know there's DNAPL, and you've got to allow for some source to be dealt with. So it went deeper, went about 10 meters below ground level. It affected the groundwater. It is in the form of a dense non-aqueous phase liquid, and it's in a low permeability setting. A natural formation. However, there was also another plume on the site, and this was within the perched water, within the granular-made ground just underneath the slab, perhaps a meter deep, and then sitting on top of these tight clays. The spread of the contamination in here was much lower concentrations. Probably the extent of it was due to the initial flush of the spill, but also through diffusion and basically perched water moving across the site. It was quite flat, the top of the clays in this area. So we're dealing with mostly a few hundred micrograms per litre. In some places it was up to 16 milligrams per litre PCE. So you are dealing with globules of DNAPL. There is potentially some DNAPL. And on a potentially what you would call a normal site, 16 milligram per litre might be considered high, but considering the other concentrations we've got at this site, it wasn't the main area of concern, but we did need to treat that. And do remember, this part of the plume is now actually underneath the active facility. Okay, so shallow, it's in the perched groundwater, and it's in a high permeability made ground. So we've got contamination both deep and in low permeability zone, and shallow in a high permeability zone. So the remediation solution for the clays, the previous consultant had been looking at the site. Very little evidence of reductive dechlorination going on, and perhaps a little bit of DCE and vinyl chloride being produced, but very, very gradually. So they took the view that you wouldn't be able to rely on monitored natural attenuation, and potentially you couldn't enhance the natural attenuation. So it led to a development of an excavation strategy. As George mentioned, this would have been an excavation right up to the edge of the building, between the building and the outside edge of that backyard on the right there, the red line. And this would have gone down potentially 10 meters. So it's quite confined, it's very deep. You'd be looking at sheet piling right next to the building, which is quite an old building. So I think you'd probably be potentially looking at structural issues with the building there. You've got the health and safety implications of, I would have thought you'd have to put an excavator in the bottom of the excavation, which is not where you want to be. And also it's going to be extremely disruptive for the property owners. They are still wanting to run their business, and as well as spending all this money on the remediation, they aren't going to be able to do what they want to do in all that time, because the deliveries won't be able to come in and out. And also, it doesn't actually address the contamination in the shallower zone which is underneath the building. So with HIDA, we developed an alternative in situ solution. It was a single injection of hydrogen release compound, which we call HRC, mixed with HRC primer and HRCX. Now I'll come on to what those products are in the next couple of slides. Essentially, it stimulates enhanced reductive dechlorination. The products are low volume, so we use these particular products for this part of the site because it's a low permeability, so you're not going to be able to get a very high volume product in there. You pump the product in the ground, it will move perhaps 1.5 meters from the injection point, and then it will diffuse the active ingredients beyond that point to give you interlocking radius of influence. So what we used was a fairly tight injection grid of about 3 meter by 3 meter, which resulted in 32 direct push injection points, and I'll show you some pictures of how that happens later on. And basically we injected from 2 to 3 meters below ground level where the top of the groundwater was to about 9 to 11 meters below ground level, which was where the bottom of that sandy lens was. And this was based on dipping the site to see where the groundwater was across the site, but also looking at the logs as well to ensure that we targeted those sandy lenses where we think a lot of the DNAPL was residing. So hydrogen release compound, it was created in 1998 in order to deal with chlorinated solvents. It's now been used on about 2,000 sites worldwide. It looks like honey, smells like maple syrup, but it's neither. It is a food-grade material, and I'll come on to in the next slide how it's constructed. It was designed specifically in our laboratories for the treatment of chlorinated hydrocarbons. It's not a waste product. It was designed specifically for this, and it was designed on the back of the problems with very soluble substrates, which often led to expensive remediation programs, methanogenesis, vinyl chloride store. The idea behind HRC is that from a single injection, you get a controlled release of dissolved hydrogen into the groundwater for a period of about 18 months. So from one application, remediation program can last 18 months or more, and you're not disturbing the site anymore. Okay? We also mixed in HRC primer. It's a less condensed version of HRC. What it does is rapidly acclimates the aquifer down to the correct redox conditions for the reductive dechlorinating microbes to outcompete other microbes in the consortia in order for the HRC to be more effective. We also applied HRCX, which is a more condensed version of HRC. It's an extended release of hydrogen, and we use this product when we suspect there's DNAPL on the site. So you maximize the rate of reductive dechlorination using the HRC. Usually it's an increase of orders of magnitude in terms of the breakdown rate that you would get naturally, or in this case it was stalled to actually breaking down. And it maintains that degradation for a period of up to about 5 years, normally way beyond the validation period of the treatment. Normally these sites are closed within 12 months, 18 months or so, but it means that any residual contamination will still be broken down because you've got an active ingredient in there beyond the validation period. This is the HRC molecule. It's a polylactate ester. What we've basically done is we've condensed a lactic acid onto alcohol by removing water. So there's an ester bond there. And you repeat the process so you get tetramers of lactate on a carbon backbone. So you create this molecule by taking water out through condensation reaction. What happens is when you put it into the groundwater, it's now rehydrating. As it's rehydrating, those ester bonds begin to break, and it provides lactic acid into the groundwater. And we've done this in such a way that we know it will do this over a period of about 18 months. So then this product will break down, and at the end of the 18 months, there's essentially nothing left over from the HRC in the groundwater. So it dissolves. The first stage of the HRC remediation process is microbial, but it's not the microbes that you're using to break down the chlorinated solvents. What happens is the lactic acid is fermented, which is essentially part of the rotting process. So it breaks down into another organic acid, so lactic acid, pyruvic acid, acetic acid. As these microbes break down these organic acids, they produce a waste product, which is hydrogen, dissolved hydrogen. That hydrogen goes into the groundwater and provides an electron donor, which drives enhanced reductive dechlorination, which is carried out by reductive dechlorinators. Going into that a little bit more. Enhanced reductive dechlorination is a redox reaction. It's a respiration reaction whereby a microbe cascades an electron from an electron donor to an electron acceptor. There's energy given off by this reaction, which it absorbs to grow and live and create more microbes. It's exactly the same process that we complete every day by eating food, breathing oxygen. Enzymes in our gut react these two things together, release energy that we absorb. They're doing the same thing. So in this particular case, we're adding the hydrogen through the fermentation of the HRC into the groundwater. That's the electron donor. And then there are a lot of naturally occurring electron acceptors in the groundwater, such as oxygen, nitrate, iron, sulfate. And then there's also the chlorinated solvent. So you might put this hydrogen into the groundwater, wanting to get rid of the chlorinated solvents, and it's used to get rid of the oxygen. It's used to get rid of the nitrate. So what you have to do in terms of monitoring these sites, when you're assessing how much product you need to use, you need to assess all the other competing electron acceptors, which was a key part of what George did on the site, so that we can work out stoichiometrically what to use. And also we can use the HRC primer to scour away the oxygen, scour away the nitrate, and drive the process of reductive dechlorination more efficiently. So if you look at the bottom of the screen there, enhanced reductive dechlorination, we started with perchloroethylene, so PCE. It's got the 4 chlorines on it. What the reductive dechlorinators will do is snap off a chlorine, attach the hydrogen. There's energy given off by that reaction, which they absorb. They grow more reductive dechlorinators. They basically begin to outcompete all the other microbes in the consortia, and they dominate the consortia of microbial activity in the groundwater and degrade the contamination. So when that happens, you've snapped off 1 chlorine, so you're left with 3, so you create TCE. The same process happens. It snaps off a chlorine, it creates DCE, then vinyl chloride, then ethene, ethane, and essentially it results in full mineralization. So the process whereby the HRC degrades and is gone, fully mineralized, also the chlorinated solvent is gone and fully mineralized as well. So these are the expected breakdown products. This is what you might expect to see on a site. In between those 2 dotted lines is where the injection of HRC has taken place. The redox reduces. You're normally looking at getting the redox down to something like minus 150 to minus 200 millivolts. The PCE will then start to break down. The breakdown product from it is TCE. So you might see the TCE start to increase, but it's a dynamic system. That TCE is actually being broken down at the same time as it's being produced. So you'll see it increase a little bit, but then as the PCE runs out, there's less TCE being produced. So you start to see the concentration of TCE tip over the edge and head back down again. Now TCE breaks down more rapidly than its daughter product DCE, so what you might see is an increase in DCE higher than the TCE. So that's just that you're just seeing that dynamic system that the TCE is being rapidly broken down. Now vinyl chloride will break down in these anaerobic conditions. You tend not to see a large increase in the vinyl chloride at all. It will be broken down as part of the process from a single injection. Okay? We've got ethene on there as well. It's in a dotted line as well because you tend just to see wisps of ethene because it tends to break down so rapidly. Do be aware that ethene is not on your standard VOC suite, so you'll have to ask for that to be monitored for as well. It's important to check for that because it just shows the regulator that you are getting full mineralization of the chlorinated solvents on the site. Okay, so the remediation solution in the made ground, this is underneath the building in the shallow highly permeable zone. This was targeted with a version of HRC called 3D microemulsion. Okay, again, it stimulates enhanced reductive dechlorination, but we use this here because it's a high volume product, and this is a highly permeable formation. So what we can do is we can spread the injection points, which is important because it reduces the cost on the site, it reduces the amount of time we're on site, but it's particularly important on this site because we're going to have to go inside the building and do the injection, and there are a lot of machines in there, so we couldn't get a tight grid in there anyway, and we want to have interlocking radii of influence from the injection points underneath all these dry cleaning machines, etc. It also minimizes the amount of time that we're in the building doing the work. So it's a 5 meter by 5 meter grid, 22 injection points. These internal works were done on an evening and a weekend, so we didn't affect the business at all. We also injected along the bedding of the drains where a lot of the contamination had run. What we did is we plugged the drain, we injected at 3 points just underneath the drain onto one side. The 3DME basically found the bedding because it's highly permeable and filled that up. There will be been some residual DNAPL sitting in that bedding there. Any of the 3DME that got into the drain we basically washed out, and then we opened up the drain once again. So 3D microemulsion, it's a high volume version of HRC. It's a 3-stage electron donor. So the first stage essentially is some of the free lactate used in making the product. That behaves a bit like your HRC primer. It'll only last about 3 months or so, and that'll be used to acclimate the aquifer down to the correct conditions, try to take away some of those competing electron acceptors. The second donor within the product is actually the HRC molecule. If you look at the picture of the 3DME, 3D microemulsion molecule there on the left, look at the bit on the right, that's actually the HRC molecule there. So that gives you an 18-month release of hydrogen into the groundwater. And then what we've done is we've tacked on, again through condensation, through ester bonds, some fatty acids there on the left. And these will break down over about 4 to 5 years or so. Generally, we have a lot of good data up to about 2 years or so, but most of these sites are finished within that time. So we have a few sites where we've got data on there, but we've calculated and we have seen activity up to about 4 to 5 years in terms of donor release. If you look at that molecule then, it's got a lipophilic end on the left where there's the fatty acids, and a hydrophilic end on the right, which is the HRC. This essentially makes the product its own emulsifier. You know, one end wants to be in the water, the other end doesn't. So when you put it into the groundwater, the lipophilic ends, once it reaches the critical micelle concentration of 300 ppm, those fatty acids will all align themselves together, and you'll get tiny little micelles, little balls of 3DME being produced. Now these are about 0.01 to 0.05 microns, so they're absolutely minute. And that means that when you get to site, you mix the product up into a high volume, these tiny little balls of product, you inject it in the ground, and it will go a long distance. It will give you a wide distribution. It doesn't rely on emulsifiers, which would be stripped out. If you've got an emulsion and you run it through a sand filter, the first thing that happens is it strips out the emulsifiers. In this case, the product is its own emulsifier. Okay? What happens is, when you inject it, it will go a few meters, and it will still strike the soil, the clay, whatever it is, the formation, and stick. But it has an appropriate hydrophile-lipophile balance. Now the HLB, the hydrophile-lipophile balance, is a way of looking at the relative strength of the lipophilic end and the hydrophilic end of a molecule. And what that determines is how strongly it will sorb and how readily it will dissolve. Okay, so what we want to do is create a product that will transport but will stop. It won't just wash out of the site. So we want it to transport and then stick to the formation, but at the same time we want it to be soluble, so it'll then dissolve into the groundwater, because don't forget, I'm talking a lot about transportation here, but we want the product to be in the groundwater, fermenting and driving enhanced reductive dechlorination. So we call this self-distribution to get a very wide radius of influence. Basically, you inject the product, the micelles move a few meters from the injection point, they will then stick, they'll then dissolve into the groundwater again, the critical micelle concentration will be reached, it'll then mobilize again, move a few meters and stick, then dissolution will happen again, reach those critical micelle concentration again, and move itself out again. And in that way, you're driving the product through the groundwater, creating a very high radius of influence, but it's also dissolving in the groundwater and fermenting, driving reductive dechlorination. Now there's a video of this that I won't go into now, given the time, but if you do go to our website, you can just Google Regenesis 3D microemulsion movie, or just go to the 3D microemulsion page on our website. And there is about a 5-minute film on this that just, it's a bit salesy, but it shows you, it's good visualization of what's happening in the subsurface using this product. So the application, this is at the top end of the yard, where we've got contamination down to about 10 meters in the clays, where we're using HRC. So we're putting it in with a direct push rig. what you do is HRC and HRCX are quite thick, so you warm them up to drop the viscosity of the product, just reduces that pump pressure and makes the project go quicker. On this particular site, they had a steam boiler like they do on a lot of industrial dry cleaner sites, so that was useful, but you can just use heating baths, or you can use a steam lance, just add a little bit of water to the top of the product and just drop the viscosity a little bit to inject it. So those products were mixed together, then just injected in the ground. What you can see there in the background as well, the grey block is a mixing tank. You place the 3D-ME into water, mix it with a plasterer's paddle, immediately creates the 3D microemulsion, and then that pump there on the left is a high-flow multi-diaphragm pump. Because we're putting in a high volume of the 3D-ME, you want a pump that pumps a good rate so that you're not there all day, essentially. And that was injected in the shallow zone, as I've said, to go underneath the building. This is the direct push rig that we were using. Essentially, it's a window sampler on steroids. What you're using is a hollow stem steel rods. You drive those into the ground. They've got a point at the bottom to drive it in. Now, you can inject what we would call top-down or bottom-up. It didn't particularly matter on this particular site. But what you do is you delineate, or George has delineated where the contamination is. What we were doing on this site was really aiming for those sand lenses or sandy lenses. So we went to the bottom down to about 10 meters below ground level. We then switched on the pump. What this did was open up 4 spring-loaded ports at the bottom of the steel rods. They're just back from the tip and horizontal. So you're not injecting down, you're injecting sideways. And we injected the correct dose for that level within the site. And then you move up a little bit, inject another dose, move up a little bit, inject another dose, right up to the 2-3 meters where the groundwater was. So what you're doing is you've delineated vertically so that you can match your dose to the contamination. Now, it's always said that money spent on an SI is money saved on remediation. It's absolutely true when it comes to chlorinated solvents. You need to delineate well vertically and laterally. So we moved across the site, injected across the site, ensuring that we covered the entire plume. This is us doing an injection within the property itself. You can see where there's a lot of machinery in there, so we wanted to minimize the amount of injection points and also use that 3D-ME so it will overlap underneath these machines. You can see we just got the exhaust from the rig going out the door there. And this is essentially the remediation in action. It's kind of boring, isn't it? But that's the good thing about in situ remediation. We were essentially there 2 weeks, put the product into the ground, and then George's team came in over 18 months to 2 years, and all that was being done was someone coming to site and doing the monitoring. So it was very much low disturbance for the site. The project itself cost £170,000. If you compare that to the excavation, which would have been millions and would have been very dangerous, it's a very good project. So I'll come on to the results. I just want to show you areas where we had low levels of contamination and where we got to, and areas where we had high level of contamination. So in the shallow groundwater, this is in the perched water within the made ground. We started with quite a low baseline, you can see there. These are micrograms per litre you're looking at. Now, when you inject the product, you can get a movement of contamination into the groundwater. This is caused by disturbance just from injecting something into the ground. It's caused by an increase in the biomass in the ground. These microbes will create biosurfactants to drive the contamination into the groundwater where they can actually feed on them. And the other thing that happens is every time you break down a chlorinated solvent, the daughter product is slightly more soluble than the parent compound. It still doesn't want to be in the groundwater, so it will partition back into the globule of DNAPL that it came from. But what it's done is it's just cut that globule of DNAPL back with something that is more soluble. So that globule starts to break up into smaller globules, you get higher surface area, and the process accelerates. And you break down the DNAPL and bring that into the groundwater. So in this case here, you can see the PCE, which is the dark blue. At the start, there was no natural reductive dechlorination going on at all. That then breaks down over time and is almost gone at the end. In fact, in the August result, we got absolutely nothing in the groundwater, so it's rattling about very little concentrations at that point. You can see TCE is produced for the first time, and then that degrades and is gone. The DCE increases, and you can see that's on its way down by the end of the project, and vinyl chloride is being produced. You can see the vinyl chloride is not being produced in huge amounts, it's not being left on the site, it's breaking through, it's breaking down into ethene, so you're getting full reductive dechlorination on the site. In the deep groundwater, and slightly more dramatic, you've got, we're micrograms per liter again here. So the sampling shows about 50,000 microgram per liter at the start. A little bit of reductive dechlorination just stalled at that DCE and vinyl chloride. We apply the product, we know there's DNAPL in there, we drive that DNAPL into the groundwater where we can treat it using biological degradation. That PCE then breaks down, and in 18 months the PCE is down to non-detect. You can see the TCE increases. You don't get a lot of TCE because it's being broken down so rapidly, but the evidence for it having gone through that transition is that you get a build of the DCE, which is being broken down from the TCE breaking down. It's being produced from the TCE breaking down. So your DCE increases and then decreases, and you can see that disappearing. Vinyl chloride's being produced. Now look at the concentrations of the parent compound compared to how much vinyl chloride we're producing. So this vinyl chloride doesn't build. It didn't escape from the site. It was all dealt with within the treatment zone itself. You're getting ethene being produced at the end there, so you're getting full mineralization. And that allowed closure of the site within 2 years. I think it was finally negotiated. So in conclusion, in situ remediation was successful despite the high concentrations, the presence of DNAPL. So enhanced reductive dechlorination, basically a bioremediation treatment, is able to handle DNAPL. It happened under an active property, a busy facility, without pump and treat equipment, with very little people being on site, very little disturbance. There's variable permeability, highly impermeable areas and very permeable areas, and there was little evidence of reductive dechlorination occurring at the start. It was made possible by HIDA by having a quality sampling regime, which allowed an accurate remedial design. We knew the delineation was good laterally and vertically in terms of where the high levels of contamination were lurking, and this gave us confidence in coming up with a dose and coming up with the right products for the right concentrations and the right permeabilities. So this avoided very expensive excavation works, it avoided disruption to the client's business, and it gained regulatory sign-off. Okay, thank you very much. I think we'll move on to some questions now.
Okay, thank you, George and Gareth. We've had a number of questions flooding in throughout the event. We'll go through as many of those as we can. While we're printing those out and collating them, I'd like to start by asking a couple of general questions to Gareth and George. And I think the first thing I'd like to say really is that, well, Gareth, George, you're both remediation professionals. You're working on many different sites, dealing with many different contaminants. So why did you select this project to present a case study out of the various ones that you've got? Who'd like to go first? George.
As I said in my earlier presentation, we came to this project sort of midway through, really. We were asked to undertake a peer review of the previous consideration that only an excavate and replace would be successful. So I think it was the recognition that if you integrate the conceptual model with the issue of enhanced rate of degradation, then that should be fed back into your risk models. And I think that's the aspect that we recognized that the other consultants perhaps would have known about, but for one reason or another didn't really consider. And it's the sampling that we brought to the project and the consistency and the quality of that data that I think is and from the feedback Regenesis have given us, that's what stands out. So that's why I've agreed to be involved and presented today. And it's a very successful outcome for the client. So in what were quite difficult circumstances, I think.
Gareth, have you got anything to add to that? Why this case study? What's special? So what?
Yeah, thanks, Jeremy. For me, I think it answers the question of can you deal with DNAPL using enhanced reductive dechlorination? And actually it's something that we do all the time. If you look at the solubility of these chlorinated solvents, a lot of the sites that we deal with, we're dealing with little bits of DNAPL on these sites, on every site. In the source areas on this site, it's quite an extreme example, so that's why I wanted to show it, that you can deal with even levels of this kind. Also, to me, it shows the advantage of in-situ remediation using injectable substrates. You know, these people didn't get into dry cleaning because they want to clean up the groundwater. They want to get on with their job. So we can put this product in the ground, HIDA can assess how it goes, and it will remediate the site with us without us having to affect the business whatsoever. The other good thing is, coming back to how HIDA have done the monitoring on this site, it's produced some very reliable data in terms of baseline data, but also monitoring throughout. And I look forward to taking this forward and perhaps putting out a paper where we can get into a bit more and watch how all the naturally the M&A parameters change. It's a very exciting site in terms of showing good evidence of what's going on in the subsurface.
Thank you, Gareth. A number of folks have written in and asked how much it did cost and what were the alternatives. I think you touched on this, but very briefly, George, can you comment on what the alternatives were that you looked at and why this was chosen?
Okay. Yeah, as I said, we inherited some good work. The remedial trials had been run by another consultant. They'd run soil vapor extraction, they'd run considerations of pump and treat, and clearly and had got a landfill tax exemption at the time. They concluded that an in situ remediation by a physical method such as soil vapor extraction wouldn't work in this instance because of the low permeabilities of the glacial fine sands and silty clays. So that most options other than dig out had been closed out by the time we came to the project, and therefore it was really updating the conceptual model with the enhanced rates of degradation that I think just signposted that provided a product could be injected that would achieve that enhancement of the rate of degradation, then the risks for this project would be fully addressed, and thereby the client's liabilities for future off-site migration. And that was really the crux of how the project kind of signposted itself from that point, really.
Thank you, George. Couple of short questions. Does the technology degrade 111 TCA? Obviously another common, another dry cleaning agent, or Tipex thinner, of course. Yes, it does. There are a number of projects of trichloroethane treatment as well, which we're happy to provide as case studies or to talk about if necessary, but I'll keep that out of the webinar questions itself. Another question that we have here is to do with the vapors into the building and the potential of vapor intrusion, and whether this was an issue, possibly from the parent compounds themselves. Possibly the question is thinking about the daughter products and perhaps vinyl chloride. I'll pass over to George to comment on this, but I would comment specifically that when we've looked at this on other sites, other dry cleaners and spills adjacent to residential properties, on a number of cases the client has elected to undertake vapor monitoring in the space in the VADOS zone throughout the course of the project, with a view to being able to put an active extraction system in place. To date, those measures have never needed to be taken. We've not seen those levels of vapors building up in the subsurface. That's a general answer, but specifically to this case study, George, let me ask you the question. What about vapors?
Yeah. Yes, the local authority did ask us to undertake a vapor risk assessment. And clearly there's, the product had been in the ground for 20 years underneath this industrial complex. So in terms of a pathway to the site directly above, as most industrials, there's a good concrete floor. They were also still active dry cleaning, so they had health and safety monitoring for vapors as part of their process. I think if you were looking at a site where there were residential properties close to a migrating plume, then yes, you should definitely assess not only the contaminant you're starting with, but have a view as to the degradation products that will be produced and the different vapor pressures and the different risks. So for this project, it was self-taken care of by the nature of the premises, but I think that would be part of a good consideration for off-site risk if other circumstances dictated it.
Yeah, just adding to that point, it's something that we're often asked about, and some of these projects where you're next to residential properties or there is a concern for vapor from the actual remediation process, it is worth monitoring for vapor, but we tend to suggest that a conversation is had within a few months into the process, whereby you can reduce the amount of monitoring going on, because it is absolutely our experience that the degradation process doesn't create an increase in vapor in terms of methane, carbon dioxide, etc. You do get methane being produced, you do get carbon dioxide being produced, but the redox we're aiming for keeps you just above methanogenesis to keep it very efficient. The carbon dioxide being produced is in very small amounts, so it tends to be just dissolved into the groundwater itself. So the short answer is you're not getting problematic gases from the remediation process itself. Remember, this is a process that takes place over about 18 months. You're not basically blasting this off in a couple of weeks or something.
Yeah, George Flower. Yeah, I'll just very quickly run through some of the other questions that have been raised about the sampling and the response zones in the wells. The wells were installed by the previous consultant, so they were quite wide response zones. We chose to place the bladder pumps at 2/3 the depth of response zones and target those to where the most significant pollution had been found, so to target the sand lenses. So another question, a couple of questions are resulting from use of peristaltic pumps. Off the top of my head, I can't remember the exact Environment Agency guidance, but a peristaltic pump clearly works by producing, squeezing a tube at the surface and producing a vacuum. So it pumps by a reduction of atmospheric pressure on the water sample. So I think inherently it's not just by the physics of it, it might result in ethene perhaps being reduced in concentration because it will evolve from the groundwater sample. I've not had experience of running those and comparing it with the bladder pump, but it's an interesting point, but I'm not sure it's the favoured sampling solution for this particular contaminant.
Thanks, George. A few very quick questions because we're almost close to the hour and we wish to finish broadly on time. I think one question that covers a number that have been asked is this a one-off project? How representative is it? Well, let me answer that and then see if there's any quick comments the others would like to say. It's a good case study. It's not unique in case studies on our books, at least, for high concentrations in low permeability for chlorinated solvents. We've done over 2,000 chlorinated sites over the 14 or so years that we've had HRC and its family. Many of those have had concentrations which are well above the levels indicative of DNAPL, so it's not particularly unusual. So it's not a standalone project. It's a reasonably good example, but I think what is important about this one is just how well it was characterized by Haida with the baseline work and what was going on. That rather moves on to one of the other questions that we've got, is that the contract was a risk-based contract. The work was undertaken at risk on pay for performance. So let me ask Gareth this. There was risk on this. How did we know it was going to work?
You sound like one of my clients. We're confident in our products. We know that the products work. When you look at site investigations, especially chlorinated solvents, remember these chlorinated solvents, they can travel quite far, they keep going down, they don't want to be in the groundwater. So it comes down to confidence in the site investigation and whether we can really quantify what's down there. And in this case, with both site investigations that were done, but particularly with the work that George did in terms of what the other parameters were on the site, the vertical as well as lateral delineation. There was a lot of thought went into it, and give both ourselves, HIDA, and the client the confidence to push forward on this site and know that we were going to hit targets.
Thank you. And finally, Gareth and George, one general question to close, and do be brief if you can. Let me ask this. As environmental professionals, what do you consider to be the principal take-home lessons from this as a case study? Again, be brief if you would.
Yeah, George, from my point of view, it's recognizing that groundwater sampling is not so simple. The sampling method will always influence the parameters that you obtain. I think it's important to design your groundwater sampling with those chemistry and physical parameters very much in mind, because you're relying on those to inform the risk, and therefore you're relying on those to set the risk-based objectives. If you overestimate the risk, then you're closing out opportunities for successful completion. And also be aware that there's no magic way of getting rid of contaminants in the ground. You will always have to inform what can actually be achieved. I think that's very important to recognise as well.
Yeah, I want to point out that enhanced reductive dechlorination can go from very high concentrations right down to non-detect. Even on sites where you aren't seeing dihalocoides, you know, microbes grow exponentially, which is pretty quick. If you give them the right conditions, you can break down this contamination without disturbing the sites. So that's really my take-home message on this one. I'm going to hand back to Jeremy for a wrap-up, but I know there's a lot of questions, and we're not ignoring them. There's some highly technical questions in there that would take about 20 minutes to answer each question. So what we're going to do is get back to you on those ones for definite. Jeremy?
Thank you, Gareth. Yes, and questions are still coming in as each answer spawns more questions. Do please continue to type questions as long as the webinar remains open, so you've got about 5 minutes. We will address the ones we haven't answered within a target of 48 hours. So I guess that's by the end of the week if we possibly can, but it depends how fast you're all typing now. And we'll answer them to as best as we wish, as best as we're possible. If you do wish to ask the questions more publicly, there is a LinkedIn discussion about this webinar that you'll find by searching for me, Jeremy Bernstingle, on LinkedIn. If you can't find it, send a quick email to Regenesis and we'll send you a link back to that discussion. You can ask the question publicly if you prefer. Otherwise, feel free to get to us privately. With that, we've just completed the hour of this morning's webinar. I'm very pleased that you've been able to join us for this time. I hope that we've been able to provide some information that's of interest and value to you as professionals across the industry, and would hope to continue to provide additional information or clarification should you wish. So with that, I'll close this morning's webinar. Thank you all very much for attending.